let us start our linear algebra. But first of all, what is linear algebra? So really, you will see a little bit later, so I will be giving you examples and you will see it, so that this is this part of math is used practically everywhere. So starting from physics and other branches of math like numerical analysis, just everywhere, really. But why it is so? Because it starts originally, and this is where we will start, from solution of so-called linear equations. In order to introduce them, I will just write the definition, and then we will discuss this definition. So first, this definition can look a little bit abstract, but yeah. By the way, I will try to follow the book as close as I can, so that if you will miss something in a class, so you will be able to just look at the book and just reconstruct the part which you missed and so on. So I will try to follow the book closely, but also I will be giving some different examples and just some examples of applications which will be extra with respect to the book. Okay, so definition. A linear combination of variables x1, x2, xn has the form a1 x1 plus a2 x2 plus and so on plus an xn, where numbers a1, a2, an belong to this set of real numbers. So really, all the same can be formulated for complex numbers as well, but and most of the results which we will formulate with slight change, slight adjustment can be formulated for complex numbers. So in this course, I will concentrate most of the time on the real numbers. So these numbers are called the combination coefficients. A linear equation, so combination coefficients. A linear equation in the variables x1, x2, xn has the form linear combination as before, equals to some number d, where d belongs again to the set of real numbers. Just remember that and is a constant. Okay, an n tuple S1, S2, Sn. So, which belongs to the n-dimensional real space. So, is a solution. So don't worry, we will talk about this definition and go through the examples and so on. Is a solution of, or we will say it satisfies that equation if substituting the numbers S1, S2, Sn for the variables x1, x2, xn gives a true statement. So in other words, if you can write A1 S1 plus A2 S2 plus and so on plus AN Sn equals to D, and this is a true statement. Okay, a system of linear equations. System of linear equations. A11 x1 plus A12 x2 plus A1n xn equals to D1 A21 x1 A2n xn equals to D2 A m1 x1 A m2 x2 So sometimes also people write this curly bracket in order to emphasize that this is a system, not just separate equations. So a system of linear equations has the solution S1, S2, Sn if that n tuple is a solution of all equations. So, in other words, so just this expression is called a linear combination. So we can fix, so usually we are given these numbers, which are coefficients of the linear combination, and x1, x2, and so on till xn can change. Now, we can set a linear equation when we say that this linear, we want to require this linear combination to be equal to some number d, right? So then, this will be called a linear equation already, because we equate our linear combination to some number d. So solution of this linear equation is a set of such numbers s1, s2, sn, which when substituted into this linear combination, like here, will give you a true statement, which means that if we substitute instead of x1, s1, instead of x2, which is a kind of unknown, s2, and so on, so we are solving this equation. So this is true, okay? So if we consider several linear equations, in this case m linear equations, so pay attention, all of these equations are in general different, right? So pay attention that I use the following notation agreement, that this first index is the number of the equation, and second index correspond to the what x I have to multiply by this coefficient. So for example, here it's first equation, coefficient at xn, right? And here I just number also just according to equation, to the number of the equation. So altogether I have m linear equations, and I want to find such set of numbers x1, x2, xn, which satisfies these equations simultaneously, which means that if I substitute here x1, x2, and so on till xn from the solution, or if you like s1, s2, sn, like it's written here, so then this statement will be true. But the same set of numbers has to satisfy also this equation, and so on till the last equation. Okay, so that easy. So essentially, this is a linear equation. This is a system of linear equations. So I will sometimes use curly bracket to say that these are not separate linear equations, but they are all together, and we want to find such solution s1, s2, and till sn that satisfies all of these equations simultaneously. Okay, any questions? Or should I just start the examples? Okay, perfect. Okay, the simplest one is, let me consider the following simplest linear combination. x1 equals to 1. So could you tell me what will be the solution? So what has to be s1, for example?
x1 equals 1.
Yeah, exactly. It's trivial, right? So s1 equals to 1 satisfies this, right? Okay, perfect. Now, if I will change the coefficient, So I will use, pay attention. So it's just the case when n is equal to 1. So instead of, so let me write here a1 x1 plus a2 x2 plus and so on plus an xn equals to d, right? So in this case, d is equal to 1, right? And the number of variables is equal also to 1. And this is my a1, right? Essentially, a1, and this is my d, right? So in such a case, what will be the solution?
S1 equals 1/2.
Exactly, that easy. Right? Okay, now, what else can I do? Let me consider a little bit harder case. Just this. Pay attention. Absence of the coefficient here doesn't mean that corresponding coefficient is 0, right? Because really you can write it as like that. So we omit 1 because it doesn't give, yeah, by the way, just let me, it's a little bit too old for me to change it. So I write numbers like that, okay? So if you see this is 7, or this is 7, and this is 1. So these are usually the problematic things to understand, but you will get used to that really fast. Okay, so okay, if we have this, so this is A1, right? This is A2, this is D, right? Corresponding D from the linear combination, linear equation, sorry. So linear combination here, this, right? But when we equate this linear combination to some number, so we are getting already a linear equation, right? But this is already linear equation. Okay, now let us try to find the solution of that. So let me rewrite this to x1 plus x2 equals to 3, right? So let me express x2 through x1, right? Just like that. So it means that if I will, for any value of x1, if I will choose x2 according to this formula, so then it will be a solution, right? So in other words, I can write that, for example, x1 equals to some alpha, which belong to the set of real numbers, right? And x2 I can write as 3 minus 2 alpha, right? And then corresponding to tuple will give me a solution of my linear equation, this one. So if you like, we can just substitute it. So 2x1 alpha, right? Plus 3 minus 2 alpha equals to 3, right? So if you open the brackets, like that, cancel this and that, so we are getting equality always, right, for any value of alpha. Is it clear or not?
It's clear.
Yeah, thank you. Okay, now let us look at the following. let us look at the system. 3x1 plus 2x2 equals to 7 minus x1 plus x2 equals to 6. Okay, so let me first tell you that is a solution. So pay attention, when I write it like that or like that, I mean that this is x1 or s1 and this is x2, right? So what is important when I write it like that, so this is an ordered pair, right, of numbers. So because order here is important, because I need to understand that the first number is x1, supposed to be substituted instead of x1, and this number is supposed to be substituted instead of x2. So you will be asked to check whether, I mean, you will have homework problems like that, where you need to substitute x1 and the corresponding solution and check that it really is a solution. Let us check. 3 multiplied by -1 plus 2 multiplied by 5 equals to -3 plus 10 equals to 7. Works, right? So here will be -1 plus x2 5. So which is 1 plus 5 equals to 6, right? Also works, right? So this is really a solution. Is it clear or not?
Yes.
Yeah, it's clear.
Okay, perfect. Now, how to solve this type of system? So here I just gave you a solution, but really we can solve it, right? So how we do this? Idea is the following, that we can easily find the solution if we get rid of one of the unknowns, right? So for example, starting from here, I can rewrite this as x2 equals to 6 plus x1, right? Pay attention, what is important here, what I'm using here, is the following fact, that both this and that has to be satisfied simultaneously. So I can use one of the equations in order to simplify the other one. So here, for example, I expressed using one of the equations x2 through x1, right? Now, I can rewrite this as 3x1 plus 2 . So I just substituted this, right? Equals to 7. So from here I can get 3x1 plus 12 plus 2x1 equals to 7. Or I can write as 5x1 equals to 7 minus 12 equals to what?
-5.
-5, right? Because it will be 7 minus 12, right? So it's -5, right? So x5, I divide both sides by 5, and I'm getting that x1 is equal to -1, right? After that, I substitute this into here, and I'm getting that x2 equals to 6 plus -1 equals to 5, right? So I got my solution, x1 equals to -1, x2 equals to 5. Ta-da! Exactly the solution which we had, right? Is it clear or not? So essentially, you use one of the equations, you're using the fact that these equations has to be satisfied simultaneously by the same set of numbers x1 and x2, right? You use first these, for example. I mean, we could start from the first equation as well, so it doesn't matter. Just in this case, it was easier. We use this equation to express one of the unknowns through the other, then substitute it into the first equation here. And after that, we got just one unknown, right? So we brought together common terms here and got simple equation 5x1 equals to -5, right? So after that, you can easily say that, okay, x1 has to be equal to -1, right? So then, using this relation between the unknowns, you can easily find x2.
Is this a unique solution?
Yes. But we will come to the uniqueness a little bit later, okay? So, but you will see it. Okay.
Professor, can I ask a question, please?
Sure, go ahead.
So was that 2 ways to check if it's a solution, or was that whole process checking it was a solution?
No, to check that this is a solution, it was only that.
Okay.
So this process is the process of solution itself.
Finding
finding the solution. Because here, your solution was given. I essentially said that, okay, this is a solution, let us check it, right? So, and then in order to check it, you need to satisfy, substitute these values into every equation and check that all equations are satisfied, right? Like here. Clear or not?
Yes, clear, thank you.
And here I showed how to find the solution, okay? So now let us have a look at the following equation. So yeah, by the way, here, if you will try to substitute here 5 -1, you will see that this is not a solution, because essentially equations will not be satisfied. Clear? Clear or not?
Yeah, it's clear.
Yeah, thank you. So okay, now let us look at another example. (3x3 equals to 9), x1 plus 5x2 minus 2x3 equals to 2, 1/3 x1 plus 2x2 equals to 3. So system of linear equations, right? So pay attention. I don't have anything here for x3, right? And here I don't have anything for x1 and x2. So but really it's still linear combinations. So you can really write it like that. Right? So we just omit these things, the unknowns with 0 coefficients, but that's it. For simplicity, we omit them. Okay, so now how to solve it? obviously, if all these equations are satisfied, right, then it doesn't matter in what order I will write these equations. Right or not?
That makes sense.
Yeah. So let me rewrite them in the following form.
I don't understand why the order of the equations matters.
Excuse me?
I don't really understand why the like the order of the equation, the order you write the equations matter.
Really, it doesn't matter, of course. Exactly what I'm trying to say. If all these equations are has to be satisfied, right? So then it doesn't matter in what order we will write them. But as you will see later, we will be bringing the arbitrary system of linear equations into some specific form, which is easy to solve. So this is exactly what I'm doing right now. So I will bring into form which is close to that. So for example, if, as I said, because all equations, all linear equations have to be satisfied simultaneously, right? So I can use relations which I can get from one equation in others, right? In order to simplify others. For example, here. So when this equation can be satisfied, could you tell me what I know about x3?
X3 equals 3.
Exactly. So I got it from here, right? Now I can say I can substitute it into this equation, and then I will get the following. So okay, I'm not touching the first equation, just rewriting it. Right? Minus 2 multiplied by 3 equals to 2, right? So because I already used this equation, so I can just omit it for a second. So then I can rewrite it as 1/3 x1 plus 2x2 equals to 3, x1 plus 5x2. This is minus 6. If I will bring it to the right-hand side, it will be plus 6, right? Or if you like, you can say that you're adding to the left-hand side and right-hand side 6, right? Then it will cancel with these. And here it will be 8. So you see, I simplified my original system of linear equations using this relation. I got rid of x3, right? And I got system of two equations. Is it clear or not?
Yeah, it's clear what you're doing, but I'm just a little unclear about why you pick the exact order of.
Wait a little bit. You will see. Okay. You will see why. Yeah, you will see why. So essentially, idea is okay. Let me first solve this. Finally, okay. So from here, for example, I can immediately write so that x1 has to be 8 minus 5x2, right?
Yes.
So, and now I will substitute this x1 into here, and I will get 1/3 8 minus 5x2 plus 2x2 equals to 3, right? Now I have just the equation for one unknown, which I usually can solve. So 8/3 minus 5/3 x2 plus 2x2 is 6/3 x2, right? I can write it like that, equals to 3. So as a result, I'm getting 8/3 plus 1/3 x2 equals to 3, right? So, or if you like, I can multiply by 3, left-hand side and right-hand side. 8 plus x2 equals to, so, equals to 9. So from here, x2 equals to 1, right? So pay attention, I know already x3, I know x2, and now I can substitute this x2 here. So, and I will get that x1 equals to 8 minus 5. So correspondingly, x1 equals to 3. Is it clear or not?
It's clear.
Okay. Now, how else can I work with this system? Okay. So this is one approach. Now, let me come back to this. Let me come back to that. So I will rewrite this. 1/3 x1 plus 2x2 equals to 3. x1 plus 5x2 minus 2x3 equals to 2. And 3x3 equals to 9. Okay. First of all, let me get rid of this 1/3 here. Let me multiply all this by 3. So then I'm getting x1 plus 6x2 equals to 9. x1 plus 5x2 minus 2x3 equals to 2. 3x3 equals to 9. Okay, now let me do the following operation. I will justify it a little bit later. So I will multiply this by -1 and add to this. Or if you like, it's the same, you can say, let me subtract this expression from this one. Why can I do this? Because this and that are equal to each other, supposed to be equal to each other. So I'm subtracting equal numbers from left-hand side. From here, I'm subtracting this. And from here, I'm subtracting these because they're supposed to be equal, right? By condition that we have a system of linear equations, so which means that they have to be satisfied simultaneously. So when I'm subtracting these, the first equation from the second one, so nothing's supposed to change, right? So first equation stays the same. Here, x1 minus x1 will cancel, right? 0. So 5x1 minus 5x2, sorry, minus 6x2 is minus x2, right? Here is nothing, so minus 2x3. And here is 2 minus 9, right? Minus 7. And this stays the same. Okay, so what can I do in order to simplify it a little bit? So I will erase this, and then let me multiply all this equation by -1, just to get rid of these negative signs. Like that. Okay, I brought equation to this stair-like form, right? So you see, upside down staircase, right? Like that. So you remember you asked why order is important. This is why. Have a look. If I have equations in this form, so which means that here I have just one unknown. Next, on top of it, I have just two unknowns. Here I have potentially three unknowns, but in this case also two, so but I can write it like that, right? So why it's important? Because from this equation, I can immediately write that x3 equals to 3, right? Then I substitute it into this equation, and I will get x2 equals to, I mean, not like that, not yet equals, x2 plus 2x3, 6 equals to 7, right? Clear? And from here, I can immediately write that x2 is equal to 1, right? Now, I can substitute this x3 here and this x2 here, and we will get x1 plus 6 multiplied by 1 plus 0 multiplied by 3 equals to 9, right? And from here, I immediately get that x1 equals to what? Could you tell me?
3.
3.
Right, 3. So once again, we got a solution 3, 1, 3. Exactly the one which we had before, right? You remember this, and that. But what is important, that if you brought your system in this form, so this is easy to solve, right? Then you substitute this solution in the equation above, and you're getting, again, equation with one unknown, which is easy to solve. Now, for the equation above, you can substitute results from here and from here, like we did here and here, right? And again, you will get equation with one unknown, which is easy to solve. So essentially, when you brought equation into this form, using this process of subsequently solving simple equations, this process is called backward substitution. Why backward? Because you start from below, right? So you have one unknown here, easy to solve. Then you go up, make this equation again into equation with one unknown, which is easy to solve. Then you go up using results from the first two equations, the bottom two equations. You are solving the last equation. Is it clear or not? Did I resolve the question why why the order of equations is important? It's not important, it's just convenient. This is the difference. So essentially, you see, this form allows you to exclude unknowns, get rid of them one by one. Clear or not?
Yes.
Okay. Now, let me formulate the following theorem. So this is so this method of solution of linear equations is called Gauss method of solution, or Gauss reduction, or whatever. So there are different names. Gauss elimination. Because here, idea is that after you brought your system in this form, you eliminate unknowns by one, right? So you resolved for x3, so you can get rid of this and this. So you eliminated one unknown. Then after you got x2, so you can get rid of this unknown, right? Substituting there x2. And you eliminating essentially one unknown by another. So also Gaussian elimination. Okay. Essentially, statement is the following. The following row operations we will call them elementary row operations. Do the following row operations give systems of linear equations. I will use SLE, SLE acronym, system of linear equations with the same solutions or equivalent systems. So we call systems equivalent if they have the same solution set. So solution sets, equivalent system. Okay, elementary row operation number 1. We can swap two rows. Elementary row operation number 2. We can multiply any row of the system by zero scalar number. Okay, and elementary row operation number 3, we can replace a row by some of this row and a multiple of another row. So pay attention. So this is exactly what we did here, for example. Here, we replaced row 2 we said that let us replace it or assign it, or if you like, I can write it like that. Row 2, I replaced by row 2 plus -1 multiplied by row 1. So what I did, I said that I will take this row, and replace it by the sum of the row 2, and the first row multiplied by -1. Clear or not? Any questions?
Is there standard notation that you would like us to use?
I will show you notation, but you can use this one if you like. But later I will show you notation which will be similar to that. So essentially you will be writing systems of equations one by one. Okay? Okay. Now, let me prove the theorem. So, first of all, number one, because by definition, solution has to satisfy all equations of system of linear equations simultaneously, then swap or change of the order. Of the equations does not affect the solution, right? Because okay, we have a system of equations. Here it is, right? So this is our system of equations. If I have a solution, so it will satisfy which satisfies original system of linear equations. If I swap the rows, right? So it will stay the same. It still will satisfy all of the equations. Clear or not?
Clear.
Also, pay attention that these, this operation, swap of two rows, right, is invertible. I can swap them back and nothing changes, right? So I can always swap them back. So I'm not losing any information. Clear or not?
That makes sense.
Okay, number two. If I multiply by a non-zero scalar, right? So, or by non-zero number, let's say, by non-zero real number, right? So I can always divide afterwards by the same number, and because number is non-zero, division is defined, right? So, and I will bring the system to the original state, right? But what is important that, for example, if I had linear equation a, let's say a11 x1, okay, you know, I better will continue on the next lecture because it's time already, right? So I don't want to delay you, but just wanted to say that the thing is that these two operations, these two operations are obviously invertible, right? So we can start from, so for example, if we multiplied some row by alpha, which is non-zero, right? We can afterwards multiply by 1 over alpha, and we will get original equation. Is it clear or not?
Yes, for me,
Yes.
Yeah, so as a result, essentially, these two cases are obvious. This case is less obvious, and we will consider it in the beginning of the next lecture. Okay? Okay, thank you very much for the lecture.